All right, so the purpose of this quick video is to give you guys a rundown of what it was we were doing on October 13th and October 15th. I am recording this as of the 14th after we got done with our PSAT exam, but this is for students who are either missing because of COVID-related stuff, missed in general because of random just life things happening, right? Or anyone who might want a review of the notes that we took in class. So the whole class started, and I'm going to briefly go through the beginning of assignment 3. I'm not doing the whole thing. I'm not doing what I did in class. But for assignment 3, one of the biggest things that I noticed students struggling with was how to get started with these problems. And year to year, it's the same issue with almost all of physics. It's how you know what equation it is you're going to select and when you need to select it. So one of the first things I always like to do is make sure you guys are identifying your variables correctly. In this case, for number 3, we have a velocity of 38 meters per second. They slow down at this particular rate. Notice the units on that are meters per second squared, not meters per second. So that's how I know that this is an acceleration of negative 1.5. They're asking me for the other speed, the speed after this individual had been slowing for a while. And that tells me right off the bat my 38 meters per second was my initial speed. Then they give me a time of 12 seconds. And from this list of information, I'm able to then pick an equation. Notice distance isn't included anywhere in here, so I pick the one equation on the equation card or on the front of the packet that doesn't contain the value for distance. Distance has nothing to do with this problem. And so those two steps, being able to look at a problem, identify what variables were provided, and then pick the correct equation, that is physics. And one of the things that most students struggle with most are one of those two steps. It doesn't matter which one it is. And so if that's where we're getting stuck, please practice that as much as you can, right? If you didn't do any of assignment 2 so far, which some of you might not have, I encourage you to do that. If you need to put this, print off a fresh copy, put everything away and try it again, go for it. That would be ideal. I really think that is the best study tip I can possibly give, is just put it away, get a fresh copy of it, treat it like it were a quiz, and see how you improved, see what changed. So I did a bunch of these problems together with you guys in class before moving on. Number 5 is definitely one that I still want to do with you guys. And this is how I actually started it. So what we assigned for assignment 1, assignment 3, or even assignment 2, what was assigned was the same material that was on that quiz. I'm going to make a separate video going over the quiz so you guys can see all the, what the correct answer should have been and why. And number 5 is one of them I didn't ask you to do because it is our segue into the next half of this unit. We've talked about things accelerating, speeding up, slowing down. We've talked about how drop problems occur and how they start with no speed and what happens if they start from rest and begin to fall and what gravity can do. But one of the things we have ignored so far is the fact that not everything starts at rest when it falls. Sometimes people like to throw things at other people. And sometimes when you throw things at someone else, they don't start with an initial velocity of 0. They don't start at rest. And so that's exactly what is happening here. Courtney is throwing a water balloon down off the roof at Joe. And so we have an initial velocity being provided in this particular problem of negative 5 meters per second. That negative is really important because the negative gives me direction. Just like on our regular old XY coordinate scales from our algebra classes, anything below origin, below 0, would be labeled with a negative y value. In this particular case, because we're starting up here where Courtney is at, that's going to be where we set 0, always. It would be where the object begins moving is where we set 0. And in this case, that negative doesn't mean she's moving, or the water balloon is moving backwards 5 meters per second. It doesn't mean that it's losing 5 meters per second every second. This isn't an acceleration. This means that it is moving down at Joe from above to below 5 meters per second in that downward direction. That also means that the 12-meter height that Courtney has above Joe, if we start up top with a 0, that 12 meters is a negative 12 meters, and that will be important in a moment. What is the velocity of the water balloon as it hits Joe? So my final velocity is what they ask me to solve for. And there's one variable that is not included here because it doesn't need to be included. It's one of those things that we always know to be true. Lincoln Way Central, last time I checked, as well as everyone who's ever been named Courtney or Joe, maybe in orbit around, but at least all of those individuals have been on Earth. And if you're on Earth, acceleration due to gravity is 10 meters per second squared. In this case, because we are finally taking care of and addressing direction, this needs to be a negative 10 meters per second squared. That's not a number you have to memorize. It is at the top of every single page on my unit exam. Gravity is negative 10 meters per second squared. It's always going to be pulling things down towards the center of the planet. So looking at the list of variables that I have provided, I'll notice, and if picking the equation is where you struggle, this is what I want you to notice. There is no mention of how long this water balloon is in the air. There is no mention of the amount of time it takes for it to leave Courtney's hand and reach Joe's head. So I'm going to pick the one equation that I have at my disposal that does not contain the value t, or the variable time, anywhere in it. Let me erase this because that got a little messy. It should be 2AD here. Okay. Now we're going to plug everything in where it should be. Final velocity is what we're solving for. It's still going to be squared. Our initial velocity is a negative 5. This is getting squared, so we have to be careful with that. We have 2 multiplied by negative 10 multiplied by negative 12. With this information, I'm going to do a line of algebra. Normally I wouldn't do it. I need to see at least this much on a test so that I know you're plugging things in the correct spot, because that is another, not often, but another source of potential issues or places that we could go wrong. Negative 5 multiplied by negative 5 is always going to give me a positive 25. The fact that that becomes positive is important. Negative 10 multiplied by negative 12 is going to give me 120, positive 120. And I get from that a positive 240 when I multiply it by 2 again. My final velocity squared, if I simplify this a little bit more, is a positive 265. This needs to be positive because you cannot take the square root of a negative number. So my final velocity is going to work out to be 16.3, just like it says down below, because it's a velocity, it's units of meters per second, but we are not done yet. This is not, the number I have reported right here actually tells me that this water balloon, as Courtney threw it down at Joe, apparently started moving upwards away from Courtney, right? That positive in front of the velocity here means that it's moving in the opposite direction it was when she threw it. And anytime we've ever thrown anything at the ground, it doesn't matter what the scenario is, it doesn't, without hitting the ground and rebounding off the ground, which is a collision we're going to talk about second semester, it's not going to be going upwards after throwing it down, right? It doesn't change direction on its own. So this does need to be a negative. Now, Mr. Willis is not just arbitrarily assigning a negative value here to make the world work the way that he thinks it should. You need to remember that from algebra class, maybe a few years ago, anytime you take the square root of anything, there are always two possible solutions. There's the positive solution and the negative solution. So the square root of 265 can be a positive 16.3, but it can also just as likely be a negative 16.3. And in this particular case, we have to pick the negative 16.3 solution because it is still moving in that downward direction. So only thing I wanted you to notice with number 5 is that our procedures are the exact same. They haven't changed. You make your list of things that you know from the problem. Maybe draw a picture. That might be somewhat beneficial, especially now that direction is an issue. And then you're going to pick the equation that fits that list of variables you had provided best. From there, plug everything in. We get some freshman year algebra. Put a box around your answer. So the only thing that changed with number 5 is the fact that we included direction. And we're going to have to start including direction in a lot of these. So knowing that we have to start including direction, there's going to be a couple of things I wanted to talk about. Honestly, the first half of these notes for assignment 4 are what I would have done with you in class as a review after we took our quiz of, hey, this is where we have been, this is where we're going. But because we're moving so much quicker than we normally would, not that we're moving quicker, just that you guys are doing some of this on your own at home, which is totally fine, I'm going to leave this review part as something that you can work on your own at home. I will tell you, first and foremost, these two questions, 1 and 2, totally going to be on the exam. You need to know what typical units of velocity are going to be and what typical units of acceleration are going to be. It's, velocity is a distance divided by time, and acceleration is always a velocity divided by time, right? So distance divided by time is speed, and acceleration is speed divided by time, how that speed changes with time. So you need to know that your units are always going to be the same as well, respectively to those, right? Speed is meters per second. It's a unit of distance divided by a unit of time. So it matches the equation. That's what I'm trying to get at. For number 3, only a couple of things that I would encourage you guys to remember or recognize is the fact that if it starts at rest or comes to a stop at the end of its problem, then you know something about your initial and or final velocity. This is still an acceleration because it is a unit of speed divided by a unit of time, meters per second per second. Number 4, this phrase, really, really, really important, and that's where I was able to get it. This phrase, because you have a constant speed, means that your acceleration is 0, and it means that you get to use that really nice, neat, old equation that we used to have. If your acceleration is anything other than 0, like in number 5 or in number 3, you cannot use this equation. You cannot use v equals d over t because it doesn't take into account the fact that you now have 2 different velocities, and it doesn't take into account any version of acceleration for that matter. So we cannot use that equation anymore. Number 5 I really like just because it's a good example of what we were talking about on number 5, actually, ironically enough, from assignment 3. What happens in this case, we have a negative acceleration, something is slowing down, and so you should be able to work through the stuff that was from the first half of this unit there. Number 6 is where we finally get into the new material, and this is the material that I wanted you guys to be able to see. I'm going to move this just a little bit. When will the object run out of speed? So if you wanted to, you could do a really quick Google search of every single, person throwing something up into the air, or you yourself could sit at home, take your pencil, take your pen, take a tennis ball, racquetball, whatever it is you've got, toss it up into the air, and you're going to notice that the exact same thing happens every single time. You give it some initial speed, and as it leaves your hand, it doesn't gain any additional speed, more so than what you had given it. So if you throw it harder, it starts off going a lot faster. But what you'll notice is that as you throw this object directly up into the air, eventually it will run out of the velocity that you supplied it. And gravity basically is chipping away at the speed you gave it every single second until finally it reaches a point, the highest point it's going to be able to go. And at that moment, it's going to turn around and come right back down. That is a really important point. The top of this little, what we'll call trajectory, the top of that trajectory literally is telling you when the object, whatever it is that you threw up into the air, runs out of speed. So for 6A, when will the ball run out of speed? It runs out of speed at the top of the technical word is trajectory. I'm just going to say flight path. At the top of its motion, right? Up here at the very top, where I'm highlighting all that, we can write out that the velocity is going to be 0 meters per second. Whatever speed you gave it, in this particular case, the initial velocity for this ball was 50 meters per second. That was the velocity that was given to this ball originally. Now, I made it 50 meters per second because it's a nice round, even number. It's ridiculously fast. I don't know of anyone who could throw a ball, this speed up into the air. But the math works out easier in this particular case. It makes it easy to graph in number 7, and that's what I wanted. So, you have to start being particular. This velocity that we gave it, 50 meters per second, I'm going to make it a positive 50 meters per second, and you'll see why in a second, why that's really important. So you give it 50 meters per second worth of speed at the beginning of this throw. Gravity gradually chips away at that, slowing it down, acting like brakes in a car until finally its velocity reaches 0, and it took away all of the speed that you had given it, but gravity doesn't stop working. Gravity is going to turn it around and bring it right back down to where it started. That's what's happening in all of these scenarios. So if I wanted to find out what the height of this ball would have been, how high off, that's not a straight line at all, how high off the ground did this ball make it, then what I'm literally measuring is the distance or displacement that this ball has from 0 to its peak, to the maximum height of its flight path, maximum height of its trajectory. So if I were to go and actually do this calculation, let me zoom in a little bit so I've got a little bit more room to work. If I were to go and do this calculation, there's a couple of things that I know right off the bat. The first thing that I know is that my initial velocity is a positive 50 meters per second. The second thing that I know is that I have a velocity, and notice I'm going to write velocity at the top. I'm not writing VF. I'll explain why in a moment. Velocity at the top is going to be 0 meters per second. If the distance from the beginning to the top is all that I'm interested in, then I don't have to worry at all about the trip coming back down. So this is going to be what I'm solving for. It's probably going to be measured in meters because the unit of distance used in my initial velocity was also meters. But then there's also one other thing that I know, and it's the one thing that you cannot escape. It will always be present. It will always be working on you unless you wind up getting to be super awesome and you become an astronaut, at which point I'm incredibly jealous. Like, let me come tour NASA. That'd be great. I'd nerd out all day. Even if I'm 90, please let me come hang out. That'd be great. Anyways, so in this particular case, we know this set of information. We know nothing about time. We've got two velocities, a distance we're solving for, and an acceleration. No mention of time has been provided. So the equation I'm going to use is VF squared is equal to VI squared plus 2AD, because this is the only equation that doesn't contain time. Now, my final velocity is not actually the speed at which this ball stops moving or the speed it has at the end of its motion. Remember, it goes all the way up to the top, turns around, and comes back down. But what I can do, if I'm only interested in how high this ball goes, is I can take that velocity at the top and plug it in for my final velocity, because that is the final point I'm interested in measuring my distance at. That's all I want. So while I'm not going to write that my VF is 0, because technically my final velocity for this ball is not 0. When it returns to the hands of the person who threw it, it's not moving at 0 meters per second. It will be moving at a non-zero number, collide with their hands, and then obviously the collision will probably hurt because it's moving pretty fast. But the speed at the top, because all I'm interested in is the displacement from the bottom to the top, speed at the top is 0. So I'm going to plug it in for my final velocity in this particular case. Then I get 50 as my original speed. That still needs to be squared, plus 2 multiplied by negative 10. You have to make sure that 10 is negative in this case because it's working against the motion of the ball. Even as the ball is traveling upwards, and you have that velocity vector that the ball has going in the upward direction, your acceleration vector for all things is always going to be negative, and it's always chipping away a little bit every second of that speed as it travels upward. I'll explain that in a moment. So I'm going to take a step further. 0 is going to be equal to 2,500. That's what 50 squared is going to work out to be, plus a negative 20. Sorry, I forgot to write down that we're multiplying all of that by our distance. Okay, one thing I do not ever want to see, and I will see it, I know I will see it, because some of you guys either aren't going to watch this video, or you're going to be flying way too quickly through the quiz or through the exam, and you'll just make a silly algebraic error here. It happens every year. This does not simplify. 0 equals 2,500 plus negative 20d. This does not simplify to 2,480. You cannot combine 2,500 and 20 because 20 is a function of distance. As distance changes, so too does this whole term that has the number 20 in it. They are not like terms, as we would say in algebra, and you cannot combine them. So we have to move our 2,500 to the other side by subtracting it from both sides. That's going to be equal to negative 20 multiplied by my distance or displacement. Divide both sides by my negative 20, and your displacement becomes 125 meters. That's your height above the ground that this ball is able to reach. Notice also, those two negatives cancel each other out. This is a positive 125, and direction-wise, that makes sense because you threw the ball up into the air, so it's going up above 0. That is always going to be represented as a positive value. That is how we should be approaching at least the trip up. So, how long will it take before the ball is returned to the person who threw it? I'm going to zoom out a little bit so we can still see most of that diagram. But this particular version of the problem really isn't that much different. Because we're looking for time, I'm going to split this up into two parts so that you guys can see how it works independently in case you ever have to use it independently. And then I'm going to show you how it all works combined together so that you can see, once we find out what the velocity coming back down would be, so that you can see an easier way, in my personal opinion, of how to solve for the total time this thing would be in the air for. So if I wanted just the amount of time it took to go from 0 meters on the ground to 125 meters above the ground, if it wanted to calculate the amount of time it took to go from 50 meters per second to the moment it runs out of speed at the top to 0 meters per second, the easiest equation that I could use to do that is VF is equal to VI plus AT. Now, you could technically, because you know your distance, use any of the equations. I'm going to turn around and use the other equation here in a moment because I like the other equation as well, but it will get me to the same point. So my final velocity isn't really my final speed. It's just the time it takes to get to the top. So my velocity at the top happens to be 0. I still have a positive 50 as my initial velocity, plus my acceleration is still negative 10 because it's always working against that initial direction vector. And again, this does not simplify to 0 equals 40t. I see it every year. Please don't do that. Move your 50 over. You get negative 50 is equal to negative 10 multiplied by time. Divide both sides by that, and you get your time up to the top of 5 seconds. We're not done. That was just your time to get up to the top. But you figured out the first half of this particular problem. Now, I'm hoping we can make the connection that, because gravity is the only thing causing its speed to change, that if it took 5 seconds to slow down to get to 0, then as it falls back down to the same position it had before, it should hopefully be the same amount of time. But as with everything I've ever given you in this class, I'm always going to provide evidence. So I'm going to actually approach this with a different equation. I'm not going to use this because I don't know what my final speed coming all the way back down to the ground would be. That final velocity isn't something I have. There's only one equation that doesn't contain final velocity, and that is your distance equation. Distance is equal to your initial velocity multiplied by time plus 1/2 acceleration multiplied by the square of time. This is the only equation that doesn't contain final velocity, and because I don't know yet what that is, I can't use it. So I need to know the distance that this object went. Naturally, I would hope that we can make the connection that if it went 125 meters up into the air, that we would recognize that it then also, if it came back to where it started, would have to fall 125 meters down to its initial position. Right? What goes up must come down, and if you go up 125 meters, you're going to come back down 125 meters. So in this particular case, my distance is negative 125. My initial velocity, notice this isn't the initial velocity all the way back at the beginning. I'm just talking about its trip coming back down. So the speed that it starts at on its trip back down is that velocity at the top, and that is still 0. So we've got 1/2 of my acceleration due to gravity, which is negative 10, and the time that it is falling for is what I'm solving for. Notice, please, that I put t in parentheses with that square, with that exponent. Only time gets squared in this particular problem. So from here, I'm going to simplify things a little bit. I get negative 125 is equal to negative 5t squared. Divide both sides by negative 5, and you get a positive 25 is equal to t squared. And that works perfectly because those two negatives had to disappear. We have t squared. You have to take the square root of it. And you'll notice that you get a time coming back down of 5 seconds. Now, I know earlier I said that your square roots technically give you a positive or a negative value as your answer choice. You should never get a negative value of time. You cannot go backwards in time, because remember, negatives in physics mean direction. We can't go backwards in time. Mistakes you've made in the past, I've talked about a few of mine. You can't go back and fix them. So it's always going to be the positive version of it. And obviously, in this particular case, your time up is equal to your time down. That's one of the things we should notice. I'll make a whole list of things that we know about this problem here in a moment. But your total time in air, 5 seconds up, 5 seconds back down. Total time in air was 10 seconds. Notice I'm still using the same equations I've always had. The only thing I really added to this was, number one, direction, right? The initial velocity is opposite of gravity. And at the top of its flight path, it's 0. Because you know the velocity at the top, you can split this problem in half. You could talk about its trip going from non-zero velocity at the beginning to 0. Have that be your final velocity if you want to just talk about its trip up to the highest point in its flight path. Or you can do the opposite, treat it like a drop problem, right? If we start at the top halfway through the problem and we treat it like a drop problem, then you can do, find your distance that you fell, find the amount of time it took to fall. You can even find your final velocity. I'm not going to do it that way because I want to do this. I want to do this graph. I'm going to make each one of these vertical lines worth 1 second of time. I'm only labeling every other one, but that's fine. We can do that. And then your vertical lines, your lines going up your, the y-axis, for velocity, I'm going to label in increments of 10. So 10 meters per second here, 20 meters per second here, 30 meters per second here, 40 meters per second here, and 50 up at the top. So 0 is all the way down here in the bottom left-hand corner, as always. At time of 0, at the beginning of this problem, the moment this ball left the person who threw it, whoever that was, as soon as this ball left their hands, it's traveling at 50 meters per second. And let's just think about gravity in terms of what gravity literally means. It means that every second this ball is moving, gravity is adding negative 10 meters per second every second. In this particular case, your 50 was positive, so adding that negative is like subtracting, right? Every second gravity chips away at its speed 10 meters per second every second. So after 1 second of moving in the air, traveling upwards towards the top of its flight path, towards the top of its trajectory, it lost 10 meters per second. After 2 seconds, it lost 20 meters per second. After 3 seconds, it lost 30 meters per second. 4 seconds, it lost 40 meters per second. And after 5 seconds, it loses all 50 meters per second. Notice your time up to the top was 5 seconds. It took 5 seconds for my velocity to reach 0. This would be what I refer to as the top of the trajectory. I'm going to abbreviate that. It's the top of its trajectory right there. It ran out of speed. Now, I'm going to ignore direction here so you can see what happens. But after it reaches the top, now the direction has changed. Now gravity and its velocity vector are in the same direction. It starts falling back down. It starts gaining negative speed. And after 1 second, just like every drop problem, it gains negative 10 meters per second every second. So it's going, if I'm ignoring speed, or ignoring direction, so I'm talking strictly speed here, it's now moving 10 meters per second. After 2 seconds, it's now moving 20 meters per second. 3 seconds is 30, 4 seconds is 40, and after 5 seconds of free fall, right, the same 5 seconds that I knew I would have, notice it's back to its same original speed. So our final velocity is still going to be 50, but it's going to wind up being a negative 50. So there's a couple of things that I want you guys to write down somewhere in your notes, somewhere, somehow, things that we know. And I'm going to label this throw up tips. Right? I'm not talking about actually vomiting. Please don't do that. That's gross. But I am talking about things that we know going into a problem where something is thrown up into the air that you can assume right off the bat, especially in a multiple choice section, that is going to make this very, very, very easy. Maybe not easy, but a lot simpler, right? So we know that our positive initial velocity is going to be equal to our negative final velocity. What's an example of that? We know that if we start with a positive 50 meters per second as this thing got thrown up into the air, that when it returns back to where it landed, or sorry, where it left, where it lands, back where it initially left this person's hand, if that's the same height, same displacement, those two values are equal and opposite to each other, right? Your velocity going up is positive, your velocity coming back down is the same. It also makes sense that they're the same because the only thing that caused its velocity to change was gravity, and gravity kept doing the same thing at every time interval. Every second that passed, gravity was doing the exact same thing, adding, negative 10 meters per second to its velocity every second. The other thing that we know going into this, there's going to be 5 of these total, is that your velocity at the top is going to be 0 meters per second. That's another thing that you know. So we can always break the problem in half, figure out, its height, the distance to the top, the amount of time it takes to reach the top. things along those lines. We always know that gravity is going to be a negative 10 meters per second squared. That negative now is crucial. On the exam, everything will be negative 10. All of it. We ignored it before because I had everything moving in the same direction. I had set up all the problems. So those velocity and acceleration vectors, especially for a drop problem, were always working in the same direction, so the negatives always canceled. You just didn't know that they should have been negative in the first place. That's all that's changed. Now the new stuff, your time up is always going to be equal to your time back down. So if I ask you the total time that this ball was in the air for, you really would have only had to find your time up here at the very top. That's all you would have had to do, and then after that, double it. Because the time coming back down is going to be the exact same, because gravity is the thing that is still causing its speed to change. The other thing that you know, going into all of these problems, if it was provided, is that your distance or your displacement, your vertical displacement going up, is equal to your displacement coming back down. Now, you will probably need to include positives and negatives there, right? In this particular scenario, you went up 125 meters and came back down 125 meters. But this little list of 5 things are things that will always be true for every vertically launched projectile that we're going to look at in the remainder of Unit 3. So that was something that I wanted you guys to have available to you. I also want to take a quick second and show you guys another way we could have done, what problem was it? 6C, where I ask you how long was it moving up in the air for, and I said, hey, we don't know the final velocity yet. We do know the final velocity now. It is negative 50 meters per second because our initial velocity was positive 50 meters per second. So check this out. I'm going to do the same equation I did down here in 6C, but I'm going to use my actual initial velocity and my actual final velocity in this equation. And you'll be able to see something pretty neat. Your actual final velocity was 50. Your actual initial velocity, which we were using pretty much the whole time, was positive 50 plus negative 10 multiplied by your time. We have to move this 50 first. When we move that 50, we get negative 100 is equal to negative 10 multiplied by t, divide both sides by negative 10, and your time works out to be 10 seconds. This is the amount of time that it took for gravity to take your ball from positive 50 meters per second to negative 50 meters per second. So, if you remember that your velocity up is equal to your velocity back down, and I ask you for how long something's in the air for, you can literally just add a negative to the initial velocity, solve for time. If I ask you for the time of flight and you get confused by the whole, hey, the velocity at the top is 0, and that can sometimes be your initial, that can sometimes be your final, you can skip that entirely. And you can just find the total time that it's in the air for, and remember, well, half of it's going up, half of it's coming down, divide that by 2. There's your time to the top. You could do the same thing with distance. If I wanted to do VF squared is equal to VI squared plus 2AD, this would solve for the entire distance that this ball traveled, 125 up, 125 back down. When you solve for distance here, using negative 50 and positive 50 for your final and initial velocities, respectively, you'll get a distance of 250. Well, it went up 125, down 125, so you do have a total distance of 250. So, take your total distance, divide by 2. There are multiple ways that you could solve any of these problems. That can sometimes, I understand, be completely overwhelming. But that was your set of notes that I wanted you guys to have available to you for this particular homework assignment. Now, I am going to do for assignment 3, I'm going to walk you through that first one just so you get maybe a more condensed, less talking that I'm going to do on my part. Just here's the work, here's the problem. Let's walk through it together. 1 and 2 for the homework, obviously still going to assign them, but that's your old school stuff where we don't have to worry too much about direction. Everything's moving in the same direction. Number 3 is the first one that you're going to have to use direction because it's your first throw-up problem. I'm putting an X through it because I'm going to do 3A through I with you. And then really all your homework is going to be, the only new stuff you're going to see on your homework is 4, 5, and 6. And that's going to be all that I'm asking of you. That's due on Friday. What's the date? Friday. Friday the 16th at midnight on Teams, as all homework assignments always are. So a softball is thrown vertically into the air at 32 meters per second. There's a bunch of stuff I know right off the bat. First thing I'm going to write down is that my initial velocity is a positive 32 meters per second. right? We know that it's going to be traveling up into the air. It's going to reach some moment, whenever that moment happens, we'll figure it out, where it runs out of speed, falls back down to the ground, and should ideally land in the same spot. Now I spread that out horizontally just so that I can draw it easily and I don't have things overlapping each other, but it should go up and come right back down where it was. At the top of its trajectory, what is its velocity? I'm going to put this in caps. Always 0. The velocity at the top is always 0. It is in caps because that is a test question. You're welcome. What is the acceleration at the ball at the top of its trajectory? It is always not 0, -10 meters per second squared. Everyone reflexively wants to say, oh yeah, that's also always 0. It is not. Just because the ball reached the top of its trajectory and ran out of speed does not mean that the planet stopped exerting a gravitational pull, right? The planet is going to keep on doing what it's going to be doing for pretty much forever until the sun dies and swallows the planet, or at least microwaves it to the point where life as we know it can't exist. Yay! Don't worry, we got a couple billion years. We're good. Anyways, the point is, those two things, 100% exam questions. It's always going to be 0. The velocity will be at the top of its flight path, and gravity is always going to keep doing what gravity is doing, and it will be -10 for an acceleration at the top of that trajectory too. It's -10 technically for the entire path that this thing is traveling through, right? From the moment it leaves this person's hand, goes up into the air, comes to a stop, gravity wins, starts pulling it back down to the ground, and returns to the person's hand. Gravity didn't change. Always -10. How long will it take for the ball to reach the top of its trajectory? So I'm going to show you the long-winded way of this. We know the initial velocity is a +32 meters per second. We know the velocity at the top is going to be 0 meters per second. We know that acceleration due to gravity is -10 meters per second squared always, and they're asking me for time. Notice there is no mention of distance used here at all, so I'm going to pick the only equation that doesn't contain distance. VF is equal to VI plus AT. In this particular case, the velocity at the top is 0. We have a +32 plus a -10 multiplied by t. Time to the top, 3.2 seconds. What is the maximum height that the ball will reach? Well, now we're solving for distance. There's a couple of ways you could do this. I don't actually care which equation it is you're going to use. The only equation you cannot use to solve this is d is equal to vt. Can't use it because it doesn't take into account acceleration, right? There are two velocities. So I'm going to use d is equal to vit plus 1/2 at squared, now that I know my time. If you wanted to, remember my good test-taking tip is if we messed up our calculation for time, then this might not be the best equation to use. You could also use vf squared is equal to vi squared plus 2ad. That one does not contain any information that you were not provided with, but I know I did this one right. So we're going to plug in everything that we know. We've got 32 multiplied by 3.2 plus 1/2 of -10 multiplied by 3.2 squared. This is going to give me a value of, flip it over to get my answer key, 57.8. Your units are meters. Now, if you did it the other way and you used VF squared equals VI squared plus 2AD, your initial velocity squared of 32 should have given you a value of, let's see if I can find my answer key here again somewhere. Should have given you a value of, oh, I didn't actually do that. Anyways, for 32 squared, I'll do it right now for you. It will give you a value of 1,024. You move that to the left-hand side of the equation by subtracting both sides and then divide by 20. Either way, you get 57. Now, this will come out to be a positive because, again, its displacement is above 0. What is the velocity as the ball returns to the softball player's hand? Well, there are two ways that we could do that, more than two ways we could do this, actually. You could treat it as a drop problem where your initial velocity is 0. And we can do VF is equal to VI plus AT because we know the time coming back down will be the same. VF is equal to VI. In this case, your initial velocity at the top, if we treat it as a drop problem from up here, right? Just the trip back down, the starting velocity there is 0 plus negative 10 multiplied by 3.2. This works just fine. You'll get 32. It's a negative 32, but it's still 32. The other thing that you could have done, and if you want to write this on the written portion of the exam, go for it. This is what I want you to do for the multiple choice for sure. Your positive velocity up is equal, or your initial velocity, you could do it that way, is equal to your negative final velocity coming back down. And at that point, you could just report your final velocity as negative 32 meters per second. No math required. That's all I want it to be. You could do this equation multiple different ways to get that final velocity, but I think that's the easiest. Just remember that little trick that I gave you. What is the distance the ball travels on its way back down? Remember that your distance up is a positive. It's equal to the negative value of that coming back down. So your up was a positive 57. This is a negative 57. 0.8, of course. But that is all I need to see. How long does it take for the ball to return from the top of its trajectory? Again, just asking about the second half. Time up is equal to the time back down. There are no positives or negatives here. Be careful. So it's still just 3.2 seconds. Right? If I am asking you to show work, I do need to see this. Right? I understand that that is the correct way to look at it, but I need to make sure you understand that. So if you're not going to do an equation, if you're not going to do a calculation, you've got to show me that you recognize that. If you want the total time, I guess technically you could write this out as an equation. Really, all I'm looking for is that you added 3.2 to 3.2 to get 6.4. That's good enough for me. What is the height of the ball after 4.5 seconds? Oh, okay. So 4.5 seconds. This is where it gets a little weird. 0 seconds, we're down here at the start. 3.2 seconds, we make it to 0. 4.2 seconds, because 6.4 is when we get all the way back down here to 0 at the bottom, is going to be somewhere around here. So you've gone up 57.8 and fallen back some value that I don't know how to calculate that. I'm not even going to try to split this problem in half. So if you want to calculate the height of the ball, we're really just going to be using this equation. Right? This is your displacement. I don't know what its velocity is going to be at 4.5 seconds. And because I don't know what its final velocity is going to be at 4.5 seconds, this equation actually works perfectly because that d at the beginning of it doesn't stand for distance. It stands for displacement. And your displacement is your height above the ground. So when we plug everything in, your initial velocity, sure, it was a positive 32. You're going to multiply it by 4.5 because that's the amount of time it was moving for, plus 1/2 of negative 10 still, because it's gravity, we're on Earth, 4.5 squared. Now, I haven't done this one yet, not in a while at least, so let's do it together. I have got 32 multiplied by 4.5. I am going to add that, I get 144. I am going to add that to half of negative 10 plus 4.5 squared. Please make sure that 4.5 is the only thing that is being squared. And in this case, oops, sorry. I hit an addition sign instead of a multiplication sign. In this case, we're going to get, no, I did that wrong. It was 144 plus that. 42. Let me just erase it. There we go. 42.75. Notice your answer still comes out to be a positive because you are 42.75 meters above the ground. The maximum height this thing reached was 57.8. So we are indeed a little bit below that maximum height, which we knew we should be just by looking at the time measurements. But this is basically a run through of any possible thing I could ever ask you. On an exam, on a test, I would never ask you to do all of these steps all at once. I would ask one particular version of these, kind of like I'm going to do on the next couple of pages. So that was your rundown of all of the notes that we'll be talking about over the next day. So if you were absent, want a refresher, whatever, there you go. Please, 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 please email me and message me with questions, comments, or concerns.